Hi, I'm Elizabeth Hawkins. I'm a field specialist in the Department of Extension, and I focus on precision ag and agronomic systems. So today I'm going to talk to you about technology that's available to help with soil fertility management. So one of the main questions that starts to come up is when we start talking about managing nutrients is why do we want to try to spatially manage nutrients? And a lot of farmers and many of us know intuitively that there's a lot of in-field variability. You can look across a field, you know that the yields aren't going to be consistent, and that's most likely due to an underlying cause driving that variability across the field. And nutrients tend to be one of the first things that we think of that we can manage to help adjust to that yield variability across a field. We also need to think about how we need to improve our resource management in agriculture. You may be familiar with the 4R principles, which is the right source, right rate, right time, and right place. And the reason that we want to focus on these 4Rs is because we know that over-application of nutrients can become an environmental hazard. The reason that farmers do over-apply in many cases is because of the flip side of that coin, which is that under-applying nutrients and shorting that crop can be economically costly because you might decrease your yields. And so farmers in many cases are using fertilizer application as an insurance to try to buffer against that yield loss. But as we've seen in recent years across Ohio, that when issues like water quality arise, we need to really buckle down and focus on how we can be more responsible with our nutrient management. And a few years ago, this wasn't really something that we could talk about because for a while we were pretty limited by what our equipment was able to do in the field. Over the last several years, we've seen a vast improvement in the capability of our equipment to be able to change fertilizer rates on the go and adjust in shorter periods of time. Anything from a liquid application, even now to technology that allows for a variable rate of dry fertilizer is available on the market. One of the things I like to look at now that this has come available is the adoption of this sort of technology on farms. So the last time Ohio conducted a state-specific survey for precision ag adoption was in 2010. And what we learned then that 20% of the farmers in Ohio were using variable rate on about 72% of their fields. The largest portion of this variable rate was focused on fertilizer, potassium, phosphorus, and lime, but that was only about 20%. Nitrogen, on the other hand, which we know is much more difficult to manage, was only about 6%. This survey, unfortunately, hasn't been repeated since 2010, so we don't have Ohio-specific data to understand what has happened since then. Another data source that we can look at is the Crop Life Precision Dealer Survey. This is conducted every other year by Purdue University. It's a little different than the survey that was conducted in Ohio. Instead of asking farmers, they're asking retailers what their estimates are of farmer adoption. And so according to the 2019 edition of this Crop Life survey, 39% of farmers nationwide, they believe are using variable rate fertilizer. That 2017 survey, those same retailers estimated that 54% of farmers would be using variable rate fertilizer technology by 2020. Interestingly enough, that 2017 survey estimated 38% of farmers were using variable rate fertilizer technology at that time. So we're not really making much progress to that estimated 54%. So curious to see if adoption continues and we reach that estimate. Another interesting thing that this survey has been looking at is what sorts of information or what influence data has on different decision-making processes. And so in this slide, it shows the change in how much data is used, how much weight is put on data making different kinds of decisions at the farm level. And so one thing that I think is interesting is that when you look at that top row, that's our fertilizer decisions for potassium and phosphorus. And you can see that there's a large increase in the role that data is playing in making those decisions. So I think that's very heartening to see that data is starting to play a more pronounced role in making fertilizer decisions. And all of these categories are interesting, but we'll focus on those too. So next I want to talk about some of the strategies that we can use for managing fertilizers. So obviously you're going to have a different approach depending on what sort of fertilizer you're trying to manage. Phosphorus, potassium, and lime are traditionally, those prescriptions are traditionally determined by estimating soil nutrient status through soil sampling, whether that be grid or zone or whole field sampling. Nitrogen is a completely different beast. It's very unstable in the environment. It changes over time. So soil sampling isn't always a reliable way to capture the nitrogen availability in the soil. So more commonly, data like yield history or imagery is used to make nitrogen prescription decisions. So I want to talk first about soil sampling to make these prescriptions and recommendations. So this is going to be an example of you go out in the first year and you pull soil samples, and you can see in this field, this is the pH. You can see quite a bit of variability across that field in pH with these grid samples. So you can take those values and use them to create your variable rate recommendation. And so you can see in this map that we're trying to increase the pH in some of those areas of the field by applying more lime in those areas and less lime in the areas where the pH was closer to the desired level. And so then if we go back to this same field in year 4 and pull samples on that same grid, we can then see that we are, through this variable rate application, achieving our goal of raising the pH in some of those zones and making it more uniform across the field. And so this kind of gives you an idea here. You can see the 3 together. Year 1, there's a lot of variability. That variable rate prescription is designed to help reduce that variability. And then in year 4, it has worked out pretty well, and that application has helped reduce the variability across that field. So when we're talking about getting those estimates, the example previously was a grid sample, but there are 2 common methods when we're talking about identifying subfield variability that are used. And the first is grid, and the second is zone. And those soil samples are going to be taken and treated differently depending on which management approach we're going to use. So let's talk about grid sampling first. Grid sampling is a systematic approach that is designed to help us uncover that field variation. The best grid size for a field is going to depend on the level of variability across that field and the level that you're wanting to manage it at. 2.5 acre grids are very common. We are seeing more and more a movement towards what's referred to as intense grid soil sampling, which often they are referring to 1/2 acre grids or smaller. Grid sampling is the best option if you're wanting to plan a variable rate application, primarily because our interpolation methods that are used in a lot of these prescription creating softwares do rely on those equally spaced soil samples that you get from a grid sample. The biggest drawback to grid sampling is the cost. So you are often pulling quite a few samples, and you can see here in this example that just a 60-acre field at $10 a sample, which is a pretty modest price for a soil sample analysis, can get you up to $240 for a 2.5 acre grid. And if you're doing this every few years on all of your fields, that can become quite costly. The other thing to keep in mind is that the interpolation we use may give you inaccurate results if you're not using the correct grid size for the amount of variability in a field. You may be overfitting the data. But one of the nicest things about grid sampling is if you're not familiar with the level of variability in the field, it can help you uncover that variability and better understand it. So this is an example looking at a small field at different levels of different grid sizes. And so we start out here, this is for potassium, with a whole field sample. And we see here that the soil test level is 114 parts per million. And if we divide that field further, we see that that average of the whole field isn't really representative of even just the two halves. And as we divide it further and further, you see the variability becomes quite obvious. And then if you had started and made a prescription based off of that whole field sample, you would in fact be applying potassium in areas that you may not need it, and not applying potassium in areas of the field that does need additional fertilizer. So you really are perhaps on this side of the field here with the lower soil test values, not making an application that would be necessary to maintain our yield productivity. So the other common option is zone sampling. And zone sampling is popular because it is quite a bit cheaper. If you understand your field variability, you can pull fewer samples across that field. If you divide into 3 zones, you're then only sending in 3 samples as opposed to, in the previous example, many more samples. The biggest drawback here, though, is that you're going to need to make blanket applications for those zones, because now that we have unevenly spaced sample points, those interpolations that we rely on for some of that prescription software is not capable of handling those unevenly spaced points. The other biggest issue is that you do need data to identify your zone, whether that's yield data, soil type data, imagery, or using past soil samples that were sampled on a grid to pull out your zones. You are going to want to use data to make this decision. Different data layers are going to produce different zones. And so this is an example. There are lots of different types of data that are available. In this particular example, they're comparing soil electrical conductivity to the Surgo soil maps and then to an elevation map. And you can see that there is very few similarities between those 3 maps. You would potentially be determining different zones depending on which type of data you are using. And so then the question becomes, which data layer is best defining how you should be managing your nutrient variability across the field? And sometimes that answer is not very straightforward. It is important that you use multiple years of data, especially if you're working with yield data, and identify those trends over time. You do need to be honest with yourself. This is one of those yield maps that's very misleading, especially in yield data. Fertility is not always the driving cause of variability across the field. In this particular example, it is more of a topography issue, water flow in those lower yielding zones. So perhaps using variable rate for this to try to adjust that yield variability may not be your best decision. And so you can see this. This is the same field that was in the previous map, and we're just looking at that data a little bit differently. So for each of those 3 zones, if that field was divided by soil type, we've taken the normalized yield over time for 5 years. And you can see that those 3 zones do behave differently. So NAB and Cincinnati, those 2 soil type zones, over time, even though there's yield variability in that field, perform fairly consistently over time, whereas the Avenberg soil type zone jumps around. This isn't terribly surprising if you know that that Avenberg soil type zone is a clay knob. And so it's a lot more responsive to environmental drivers, rain specifically. So in dry years, that clay knob yields quite poorly, like in 2015 and 2009. But in wet years, like 2011, that can be the highest yielding zone of the field. So it becomes a lot more challenging to manage zones that have a lot more yield variability over time. So if you can identify areas in the field that have fairly stable yield responses over time, those would be your top candidates for variable rate management. And in this field, as I mentioned before, this is that topography map. And you can see that across those zones, topography and then water movement across that field is one of the primary drivers of the yield variation. So perhaps improving drainage management before trying to take on variable rate applications may provide a better return on investment. So this is some more data from that crop life survey that I referred to earlier. And this is 3 separate questions looking at soil sampling practices. The first thing that we see is grid sampling in that first graph is by far the most popular way to do soil sampling. This survey did allow multiple answers, so that's why it doesn't quite sum to 100. But management zones are the least frequently sampled practice that we see currently. It's a little disheartening that the number is so high for that whole field approach, but a lot of that is probably attributed to the cheaper cost of sending in one sample for the entire field. If we look at how zones are delineated in that next question, we see that yield maps are the top, very quickly followed by our soil map unit, that SERGO data. And so those are the 2 primary data sources that are used in zone delineation nationally. And then, as I mentioned before, 2.5 acre grids are the most common, and that was confirmed by this survey. We haven't quite seen yet here that growth in popularity of those smaller grid sizes, as the second most popular choice is larger than 2.5 acre grids. So there is a lot of technology available that can help us accurately estimate our spatial variation in our soil. And so I want to talk about, when we talk about our traditional soil sampling techniques, going out and pulling samples with a soil probe, being able to have accurate and reliable results depends very heavily on the way those soil samples are pulled. We know that pulling our samples at consistent times of the year, always in the fall or always in the spring, and not jumping back and forth, taking those cores from similar areas of the field from year to year, making sure that you're pulling your samples from both the correct depths and a consistent depths as you pull samples, and making sure you have a sufficient number of cores and you're mixing them well for your composite sample are all very important to getting accurate results. And so there's a lot of technology available that can help us improve on all of those areas. The first is GPS technology. So being able to go back to the same area of the field over time is very important to monitor trends in soil fertility. There are many apps available, a lot of them free, that you can use to navigate into an area of the field that you want to sample over time, and you can save those points. It's quite easy to take some of these and lay out a grid and have your sampling points planned ahead of time. So you can take that GPS device, in many cases these days, it's just your phone. You can take that to the field with you and navigate immediately to the spot in the field where you want to pull those samples. One step further on the technology, automated soil sampling is something that's become very widely used in the industry. This can follow a planned path through the field, and the other benefit of this approach is that it can collect very consistent samples. It's going to do a lot better than you or I could with a soil probe at pulling those samples at a consistent depth as they move across the field. And so I want to share this brief video with you that's going to show one of these samplers in action. right, so you could see from that video that it appears that he's found his point in the field, he's driving in a circle around it, and the automated sampler is pulling those cores at the same depth every time. And a lot of these automated samplers also have the ability to mix and then barcode those samples for processing. So it really streamlines that process and helps make sure that there's a level of quality control in the samples themselves. So when we talk about the intense soil sampling, this is really that next step that allows us to have a higher resolution map. On the right-hand side of that image, we're looking at 4.2 samples per acre compared to 42 samples per acre on the left-hand side. And you can see there's a very large difference in those two maps. And so we're identifying more variability, we're changing what our application would look like by having more information and higher resolution maps to make those decisions based on. This is one of those things, it is going to be much more expensive to pull more samples, but if you have a better understanding of your variability out the gate, it's going to give you a step up, and perhaps monitoring those, pulling those samples more frequently over time becomes less important, or going to a zone sampling approach becomes easier if you have this high resolution map to start from. And so one of our partners that Ohio State works with fairly frequently is Integrated Ag, and they are a retailer that does provide these more intense soil sampling. And so I want to show you a video from them talking about their approach to this intensive soil sampling.
No farmer wants to spend any more money than he has to for fertilizer. No farmer wants to do anything to put his farmland at risk. And this is just another way of capitalizing on economics plus being good environmental stewards all at the same time. What we found is the best value for our farmer is to take a sample once every 150 feet, which is a half-acre grid. So every acre receives 2 soil samples. We're using existing technology where we take the GPS to mark those locations. Then we in turn develop application maps that are much, much more accurate today that we can give to the farmer, who in turn can give to his fertilizer supplier to apply the lime and the fertilizer at a very high level of resolution and accuracy.
The patent-pending Integrated Ag Services Precision Soil Sampling System is innovation you can trust. You get more samples, better results, and higher profits. It's just that simple. For more information, contact us at integratedag.net.
All right, so that's a pretty good overview of the automated sampling process. If you ever get the opportunity to tour one of these facilities, it is pretty exciting to see the level of technology they're using from top to bottom to process these soil samples and produce these maps. One of the next things that is becoming increasingly popular is using imagery to both delineate zones in a field and then also create prescriptions. And so aerial imagery can be collected at several different levels, each of those leading to a different resolution. So when we talk about remote sensing, this data could be collected from a satellite, it could be collected from a manned aircraft, or even from a UAV. And so each of those are going to, satellite obviously is going to be the coarsest resolution, with UAV being in many cases the highest resolution. When we talk about nutrients that are applied with a prescription based on aerial imagery, nitrogen is the most common. I'm going to talk about 3 types of imagery that are commonly collected and used: RGB, near infrared, and then NDVI. And then we'll have another video that talks about a 4th. So RGB, red, green, blue imagery, is a visible color image. This could be taken on any type of camera, including your phone. This data is good to help us see shapes and definition in a field that could connect to problem areas that it's hard to see from the field level when you're walking a field. This is available from most aerial imagery platforms. and is the cheapest option. And so this is an example of an RGB image of a field, and you can see, we'll show this same field in each of the examples. But in this, you can very quickly see some of the most affected areas, in this case, drowned out spots. You can see some areas where the planter is skipped. If we talk about the next type of imagery, that near infrared imagery, this is a false color composite image that's put together that is going to show you variability that's not visible to the human eye. Plant health is one of those things that is going to be easier to see in one of these images, and oftentimes before we can see it in an RGB image. NIR is commercially available from most imagery vendors. It's typically part of the base package, but in some cases there is an additional cost. And so this is what that same field looks like with an NIR image as opposed to the RGB. And you see, you can start to see some things in this image that we didn't notice in the first image. Some areas that perhaps have had some water stress, but weren't completely drowned out. So there's a difference in plant vigor in those areas. You can also see some machine tracks across that field. The third type of imagery I want to talk about is Normalized Difference Vegetative Index, or NDVI. This is a calculated index that is commonly used to monitor crop health and photosynthetic activity. So in this case, the higher the index value, the greater the crop vigor, or the more green. This is one of the simplest indexes very commonly used by our imagery providers as part of the standard practice. It is important to note that there are two different types of NDVI image. One that is calibrated, and this is an image that you can use to show and compare differences over time, or uncalibrated, which is going to show the crop vigor in one field at a particular point in time. This is not an image that you can use and compare between fields or between years or different time points because it's not calibrated. And unfortunately, that is the most common type that is provided by imagery providers. So if you do want to be tracking changes over time and be able to compare those images to each other, you want to request calibrated NDVI images. And so here's an example of that same field again, showing it as NDVI. And you can see that there's a lot more contrast because it is that index, and a lot more variability is going to show up. So we do have at Ohio State a partner that we work with for our imagery needs in many cases, and that is AirScout. And so I want to share a video about AirScout and the products that they provide and the types of imagery that they're using.
Hi, I'm Brian Sutton. I'm the president and founder of AirScout. And I'll just tell you a little bit about our company. First off, I'm a farmer from Indiana, and that's how this whole thing got started. I was just trying to farm better and find a way to make my precision ag equipment actually work. I started out looking at a lot of different types of imagery, experimented with NDVI for a very long time. I wasn't very happy with the amount of information that it was giving me. So eventually I stumbled into true thermal, long-wave thermal cameras, and that changed things for me. It started giving me different direction and a way of creating zones within my fields that I hadn't thought about before. So we're able to manage it differently. Really what sets AirScout apart from everyone else is this thermal image. So by looking at the temperature, we can look at the differences of evapotranspiration inside that field. We see how that field is bringing up water and transpiring through its leaves. And we're able to then correlate that to the healthy and weak areas of the field. We did a little project with ENR here over the summer, and we imaged some barley fields up in North Dakota several times so that we can start to connect the dots as far as what's important and how we can read that and how to use that imagery to either grow better barley or do it in a more sustainable fashion. From a sustainability standpoint, I look at it in a way much like we do with corn and soybeans, just controlling nitrogen in the water. I think we could treat barley in a very similar fashion to how we treat corn. In other words, we only feed the plants what they need instead of just blanket applying everything from one end of the field to the other. From a seeding standpoint, we can only apply the amount of seed that we need for the particular area of the field depending on the soil type. So we can learn from that and do better from that aspect. From the growth regulator standpoint, we can apply a higher rate of growth regulator into the lush, healthy areas, and then pull back on those areas that aren't doing so well. So this will do two things. It's less chemicals that are going out there, plus it's going to allow the barley to grow better and get the right amount into the right place. We can gather an image prior to harvest, and with the knowledge that we have of the combination of thermal imagery in conjunction with our NDVI imagery, I believe we can create zones inside those fields to actually tell the farmer to go cut certain areas of these fields where they will meet spec and give you a high quality grain, and then leave some of the other places that are maybe down flat, laying on the field, and cut that and use it for amphitheater or the like. I'd like to work with AD and to learn more about that. Now we're able to truly bring in imagery, create zones that I can use as a farmer to create different management practices within those zones and farm in a much more sustainable fashion.
So they are doing some more cutting edge things using different types of images to better create these zones that we can then use. I wanted to talk about a little bit about how we're using aerial imagery to delineate zones. And one thing that we see the highest correlation with has been bare soil imagery. So you go out when your field is at field capacity, you take a bare soil image, and you can really start to see variation that is driven by factors that we know no impact fertility. And the biggest one there is the amount of organic matter. So you can see in this image on the left, those darker areas. If you go out and do some ground truthing, you'll see that there is a higher organic matter content in those zones. And if we delineate our zones based on that, that is a good baseline to start with. Especially when we're talking about nitrogen, that organic matter is a driver of both how much nitrogen is going to be naturally available through the soil, as well as how quickly it gets bound up in wetter seasons. This is also great imagery to use to help with other decisions. Drainage comes up a lot because that is one of the biggest issues we deal with in Ohio, is not enough water and too much water, sometimes in the same year. One thing to note is soil moisture is going to impact the quality and the usability of these bare soil images. So making sure that you pick field capacity is a good level, but if you're going to take these images over time, picking a consistent soil moisture level helps make these images more useful. So when we talk about using that aerial image to generate a prescription, really the nutrient where this is the most common is going to be nitrogen. And in many cases, you're seeing those prescriptions are generated based off of NDVI or something similar, false NDVI or ADVI. And those can be used to generate that prescription where we're applying more nitrogen in areas that are showing deficiency or crop stress. And so this is an example from a nitrogen trial that we were conducting in Fayette County. And you can see different areas of the field where we have some nitrogen stress. You see some past management showing up. This big red rectangle there in the center of the image is an area where we had done a cover crop trial in a previous year. And you can see that that is really impacting the crop vigor in that part of the field even now. So you would take an image like that NDVI image that I showed previously, different field for this example, but then you can take those NDVI values and where they're lower, you can create your prescription where you're applying a higher amount of nitrogen. And so here you see the change from that NDVI value on the left to the rate that's applied to that field in that prescription on the right. So I want to wrap up by talking about some of the technologies that we see coming down the pipeline, some things that folks in precision ag are pretty excited about. The first is electrical conductivity mapping. We saw on that first one of those early slides with the crop life survey data that this is a very rarely used tool in our toolbox. And so there are different types of gadgets now that you can take across the field, and they're going to directly measure the ability of the soil to conduct electrical current. And then that conductivity can be used to estimate different soil characteristics, such as texture, moisture, depth of topsoil, and salinity. This is pretty interesting data. We know things like texture is very important when we talk about nutrient management. So having a very high resolution map of those sorts of characteristics could be useful data layers for spatially managing nutrients. And so here's an example of going from that raw data to a gridded map and then to a contoured map where you can see that variability across that field, and that's a data layer that you could use if you're wanting to make a variable rate prescription. These are becoming increasingly popular. It is still fairly costly to have this kind of testing done on your farm, but you are getting a much higher resolution map, a much higher resolution data that you can then use versus a traditional soil sample. And so I'm going to show another video here that's going to talk about why mapping soil EC can be useful.
Soil EC, or soil electrical conductivity, is a way to measure soil texture, sand, silt, and clay. Texture relates to soil EC because the finer particles of clay conduct more electricity than the coarser silt and sand particles. Soil texture and soil EC matter because of the significant influence they have on the growing environment of a plant. Soil texture has a major impact on productivity, affecting water holding capacity, cation exchange capacity, CEC, drainage, topsoil depth, and nitrogen use efficiency. Whether soil will hold, lose, or use nutrients is strongly related to its texture. For example, mobile nutrients like nitrogen are leached through light soil and lost through denitrification in heavy soil. Soil EC maps define exactly where the soil texture changes within a field. With this information, growers, consultants, and input providers are devising management zones, setting sampling locations, varying seed, nitrogen, and irrigation rates, just to name a few uses of Veris EC maps.
So Veris is just one example of commercial technology that provides that type of data. Another way that we're getting higher resolution information that's similar but still different, you may be familiar with the Precision Planting Smart Farmer. So this is a planter attachment that uses an optical sensor to estimate soil characteristics like organic matter, moisture. It can detect residue in the furrow as you're planting, and then also soil temperature. And so this is, again, a type of data that's going to be much higher resolution. It's not going to have the same level of accuracy as what a soil sample is, but you have the ability to have these estimates across the field at a much higher resolution. So this is an example of what the data from a smart farmer looks like. So again, it's providing this higher resolution spatial map. This is the organic matter map for the example, and you can see the range from less than 2% to over 4% across that field. I've been doing some work with our on-farm trials looking at using this data, and it does show some potential, especially for nitrogen management. Having that ability to know or have an estimate of organic matter in many more points in the field is potentially a game changer when we talk about making nitrogen decisions. So this is an example. We had a trial, and I'm showing you very specifically in that black box on both maps a strip of the field where no nitrogen was applied at any point during the season. And you can see on the left in the organic matter map, we do have a wide range of organic matter contents across that strip, ranging anywhere from over 3% to down to under 1%. And when we look at the yield, which is what we're showing on the right, within that strip, you can see that we do achieve very different yields from one end of the field to the other. And it lines up fairly well with that same organic matter information. And so this, I think, really drives home the point that we know that we don't need the same amount of nutrient on any given spot in the field, but it does become very difficult to determine what the right rate is. And so this is a data layer that I think there's a lot of potential with some more research to help make that decision and make those decisions in a better way. So there are some companies that are hoping to bring to market some wireless sensors that you can deploy in the field. Teralytic here is an example. This sensor, you would be able, it's a probe that you could install in the field. It has different sensors on there that can estimate different things, but of primary interest, nitrogen, potassium, and phosphorus levels in the field in real time and deliver that to you telematically. This is one of those things that I think has the potential to be a game changer. As of yet, there is not currently any of these that are publicly available to be field tested, but we are the first on the list when they are. And then this is another approach that I think is definitely more of a conceptual idea. No one that I'm aware of has this in testing even, but it's this idea that you could deploy micro sensors through different, when you're making any other pass across the field, whether that be with a seeder, whether you're applying your fertilizer. But you can deploy these micro sensors that are created to last for a short time, but deliver data in real time while they're in the field. And so this is the ability, I think would give us the ability to have very high resolution data very quickly when we need to make that decision, which is something that currently we don't have a good way of getting that sort of data. So there's a lot of potential, I think, in this sort of stuff. And there's a lot of exciting technology that I'm sure we'll see over the next few years. I never cease to be shocked by how quickly technology comes and changes the way that we do business in precision ag. So to wrap up, the key takeaway points I want you to leave with are that your management strategy is going to differ by nutrient. It's just necessary. They behave differently in the environment. Therefore, we do need to manage them in appropriate ways. There is technology that has been created and helps us do a better job of collecting soil samples, and in the end brings us to hopefully higher quality data with those soil samples. But that being said, we really are still limited by these traditional approaches to estimating our variability in a field. And so I'm very excited, and hopefully you are as well, about the exciting technology that's coming on the horizon that's going to help us move from these more traditional methods and really do a better job of identifying and understanding field variability, and then making it easier for us to manage with the equipment technology that we have. So thank you for sharing your time with me today. If you'd like to get in contact with me, there's my email, and I am open to taking any questions through that method.